grade 12s, welcome to the lesson. What I'm going to be covering in this video is just a summary of this beautiful chapter, Functions and Inverses, and we're going to have a look and unpack all of the beautiful, delicious content that we've done in this section. I've started off with this slide where we can really unpack and look at, well, what is actually happening? How am I creating my original function? And from the original function, how do I form my inverse function? All right, so let's have a look at the example I have here. Now remember, for something to be called a function, we know that it must produce only one output, right? Only one y value for any given input or an x value, right? And we'll discuss that a little bit later. How do I know whether something is a function or not? But for here, we are going to take a rule, right? We are going to look at this linear function, this nice straight line. Y is equal to 2x plus 1. So the inverse of a function is a rule that follows the opposite procedure to the function itself. The opposite procedure. All right, so let's just start off with the original function. So my input, which is x, gets multiplied by 2. All right, the x times 2 to give me the 2x. I add 1, and this will give me my output value, y. Now, when I look at the inverse of y is equal to 2x plus 1, the inverse of this function does the opposite operations in reverse order. So what does that mean? So I take my input, x. All right. In the original function, I added 1. So now, in the reverse order and doing the opposite operation, I subtract 1 from x. In the original function, we were multiplying by 2. So now for the inverse opposite operation, division, I must divide by 2 to get to my output. So if I had to write down the inverse of this function, it would be y is equal to my input x minus 1 divided by 2. All right, and that would be your inverse function. Isn't that quite easy? And now if we look lower down on our slide, right, if we look at the following spider diagrams, when's the last time you did a spider diagram, grade 12s? I just want to show you that if I have the original function 2x plus 1, and I'm comparing that to the inverse function x minus 1 over 2. Let's just have a look at what happens if I input certain values into x, like what is my output? So if I choose 3x values, let's choose 0, 1, and 2. So I'm subbing 0 into x, so 2 times 0 plus 1, or that would just be 1. I'm subbing 1 into x, I'll have 3 as an output. If I sub 2 into x, I have 5 as an output. Now have a look at what happens with the inverse function, that if I choose the values 1, 3, and 5 as my input, right, the same as the values I got as an output from the original function, if I choose 1, 3, and 5 to input, can you guess what 3 values will come out here? Right? It's actually just going to be 0, 1, and 2. And let's just verify that. 1 minus 1 divided by 2 would be 0. 3 minus 1 divided by 2 would be 1. And 5 minus 1 divided by 2, well, 4 divided by 2 is just 2. So what do you notice here? The inputs of the second flow diagram are the outputs of the first flow diagram, and vice versa. And this is always the case for a function and its inverse. Isn't that awesome? Now, let's just apply a rule to all of this, because we don't want to have to do flow diagrams every time, right? Let's just have a look at the simple rule to apply throughout this chapter. So, to determine the inverse function, simply swap x and y around. So in the previous slide, I really did, the whole input procedure. What are we multiplying by, adding, subtracting? Obviously we don't want you to do that every time. We just simply want you to swap x and y around, and then we're going to make y the subject of the formula. So for a straight line, if we take that same function from before, was y is equal to 2x plus 1. If I use that rule now to switch x and y around, all right, so we'll go switch x and y. So x will be equal to 2y plus 1. Now we need to do step number 2, make y the subject of the formula. So I need to subtract 1 from both sides and then divide both sides by 2. So x minus 1 over 2 will be equal to y. That would be the equation of my inverse. Let's have a look at a parabola. So let's just choose a very simple one. Y is equal to x squared. So we know step 1, simply swap x and y around. So x will be equal to y squared. And to make y the subject of the formula, we know that we need to square root both sides. So therefore, y will be equal to plus or minus x. With an exponential function, again, let's just pick something like y is equal to 2 to the power of x. Step 1, simply swap x and y around. So x will be equal to 2 to the power of y. Now, we know here that since the bases aren't the same on either sides, right, we can't solve for y using exponential equations, but we need to use logs. So therefore, y will be equal to log your base 2 and x. All right, so here we just did 3 simple examples using your functions that we deal with in this chapter: straight line, parabola, exponential. You simply swap x and y around, and we make y the subject of the formula. Easy, hey? So here I really want us to first discuss, but what is a function? I keep saying function, function, function. Sometimes people say graph, and what actually is a function? So a function is a relation for which every x value is associated with one y value. So a relation is basically any graph, right? A relation is any graph where you can see a relationship between a set of x values and a set of y values. But a function then has to follow a specific rule. And the rule is for every x value is associated with one y value. So let's have a look at our different types of functions. So we have one x value associated with one y value. So this is a function, a one-to-one function. We can have more than one x value associating or mapping onto only one y value. That's cool, not a problem, right? One y value. So this is a function which we call a many-to-one function. Now, here's the inverse of that parabola, right? It's this arms up parabola which tips over onto its side. Whoop. Now, this is not a function because check it out. This one x value has 2 corresponding y values. So for one x, more than one y, this is not a function. Now, I've written down here how we can test to determine whether a relation is a function. So we use the vertical line test. So the vertical line test is you hold a ruler up to your graph and you draw a line, well, vertically down. And if your ruler or pencil or whatever you're using, if it cuts the graph once, right, then we know that it must be a function. If you hold your ruler up to the graph or up to the relation and it cuts more than once, right, that's when we say, all right, so that is not going to be a function. We can test this with our parabola as well, right? Vertical line only cut once by the relation, by the graph, so therefore I'm happy that is a function. So the vertical line test is what we use to determine whether a graph, a relation, is a function. So next up is the horizontal line test. So what is that? Well, the horizontal line test is how I determine I know now that I have a function, right? The vertical line tests show me that your graph was a function because your ruler or pencil was cut once. Now I turn my ruler onto its side and hold it horizontally. If your line gets cut once, right, then we say it is a one-to-one function. And if you draw that horizontal line and your graph is cut twice or more than twice, right? If you think about a cubic graph would be cut more than twice. Then we would say it's a many-to-one function. And obviously, we don't need to do the horizontal line test for our third graph, right? Because we already know it's not a function, right? If we had to call this anything, we would call it a one-to-many, right? That's how we would describe it. For one x value, it's mapping onto many y values. All right, so at the bottom here, I've just quickly done 4 graphs and I'm saying, is it a function or not? So for graph A, right, passes the vertical line test. Let's check. Yep, only getting cut once, so it is a function. And I would do the horizontal line test to determine what type of function. So this would be a many-to-one function. If I look at B, all right, so B fails my vertical line test, so not a function. For C, all right, passes the vertical line test. Then I use the horizontal line test to determine, right, so what type of function is it? It's only cut once, so this is a one-to-one function. Last one, D. So D is a circle, so I'm pretty sure you know what's happening here. Nope, not a function. So now let's discuss, so we've got this beautiful theory and background now around our functions and the inverse function. And now let's just talk about how we're going to sketch these graphs, how we're going to sketch these functions. So it's very important to know that your function and its inverse, and this is the notation that we use for inverse, right? F to the -1, not f prime like derivatives, but f to the -1. Your graphs are symmetrical about the line y is equal to x. That is very important. For every point A, B on F, so for a coordinate on F, there is a point B, A on the inverse. So remember, switch x and y around. That's how we get to our inverse. The x-intercept of F, the original function, has the same value as the y-intercept of the inverse. Very interesting. Swap x and y around. The y-intercept of f, the original function, has the same value as the x-intercept of the inverse. And what's really interesting is that all of the graphs, the original graph, its inverse, and the line y equals x all intersect at the same point. So let me just do a very basic example with you to illustrate all of these points in the slide. Cool, so we're going to draw the straight line y is equal to 2x minus 4. So that would have a y-intercept of -4 and an x-intercept of 2, right, positive gradient. So our line is looking something like this. All right, so this would be the original function f. So we set it an x-intercept of 2 and a y-intercept of -4. Right, let's get to what is the equation of the inverse. Remember, step 1 is to switch x and y around. Right? Step 2 is to make y the subject of the formula. So I'm going to add 4 to both sides and divide both sides by 2. So therefore, the equation of your inverse is y is equal to x plus 4 over 2. Now, you don't have to go about trying to determine x and y intercepts manually here. Just have a look at these two coordinates, because we know that the x-intercept on the original graph becomes the y-intercept on the inverse function. So the y-intercept for your inverse will be 2. Then the y-intercept of your original function becomes the x-intercept of your inverse. So if the y-intercept was -4, now your x-intercept on your inverse will be -4. All right, and now we just need to draw this guy. Shoo. All right, so this would be your inverse graph. Isn't that awesome? And another thing which is really awesome, check this out. That coordinate there, right, that is a shared point. All three graphs intersect at that point. The graph f, its inverse, and the line y is equal to x. Amazing. So now let's talk about reflections. Not your reflection in the mirror, by the way. Reflections about the x-axis, y-axis, and the line y is equal to x. So I've just written down the rules which we follow, right? So if you reflect in the x-axis, your x values stay the same, but your y values you're going to multiply by a negative. So if you had a point 2, 3, if you reflected that point in the x-axis, it would become the point 2, negative 3. So I've just drawn a very basic Cartesian plane in the middle of our slide here, just to illustrate the different types of reflection. So we started off talking about reflection in the x-axis. So from the point 2, 3, if you reflect about the x-axis, right, we're going to reflect over this line. It's also called the line y equals 0. So 2, 3 will become 2, negative 3. All right, so that would be a point like down there. So that would be reflection in the x-axis. Let's look at reflection in the y-axis. So we take that same point 2, 3. And what happens is your original coordinate, it's now the x value, which you multiply by a negative. So if the original point was 2, 3, the new coordinate, the reflected in the y-axis, which is also the line x equals 0, will be negative 2, 3. So that would be up over here, negative 2, 3. So we reflected over this line, the line x equals 0. So I actually think I'm going to add that in here. So remember, the reflection in the y-axis is also reflecting about the line y equals 0. And reflection in the y-axis is also a reflection about the line x equals 0. So now if we look at the last one, which is a reflection in the line y equals x, well, we know that this is where x and y just switch around. So 2, 3 becomes 3, 2. So when I reflect, we're going to be over here. All right, so that would be our new points. Okay, so reflections are quite easy, and memorizing these rules obviously means that you will just have success in any of these types of questions, correct? All right, so let's have a look at our next slide. So now we're going to talk about when we need to place restrictions on our functions. So why on earth would we want to place restrictions? So here I have the graph f of x is equal to x squared, where x is greater than or equal to 0. So instead of looking at the entire parabola, all right, my restriction given, only look at positive x values, means that, well, this part of the parabola's arm is just going to fall away, right? So we're only going to be working with positive x values. And here I've said, but like, why would I even want to do that? Right, because remember that we want our inverse to also be a function. So a parabola is a many-to-one function. Its inverse is a one-to-many, meaning it is not a function, it fails the vertical line test. But if I've chopped off an arm, like I've done here, if I restrict my domain, it means that the inverse function, well, I've just said it there, it is a function, right? Because it now passes the vertical line test. If I was to draw a vertical line there, so I know it's intersecting the black graph, but we're just looking at the inverse, the red graph. Right, we see that there's only one cut, which means that it is a function. It is now a one-to-one function. All right, so restricting the domain allows our inverse functions to be functions themselves. There's two ways you can restrict the domain, right? You can look at positive x values, or you can look at the negative x values, right? You can decide which one you want to use, or obviously just follow the question, let it guide you as to what you need to do. But restriction on functions is very important, and what they like to say is like, place a restriction on the function so that its inverse will also be a function. So you would pick, okay, I'm either going to just do positive x values or negative x values, which means now, yeah, that you can allow that inverse to be a function as well. So don't let the inequality freak you out. Remember, it's just specifying the domain which we need to work in. So I also just wanted to touch on square root functions, because I know that some of you might be looking at things like this negative under the square root sign and questioning yourself, because what have we been taught throughout our school career? We don't want a negative under the square root sign, right? We know that that is then non-real. And now suddenly we're in a chapter where you are seeing negatives under the square root sign. So I just think it's important that we discuss it. So we know that the square root of a negative number is non-real. However, any function containing a square root has restrictions on its domain and range, even if no restrictions are stated. So what that's saying is, like here, if we look at, so this is actually the function that they wanted us to start off with, then move to the inverse. I'm just going to work the other way around for it maybe to be a little bit simpler. So this was in our last slide, y is equal to x squared. We limited, or rather restricted, the domain just to look at the positive x values. Here we can see that the domain and range for this part of the parabola, x is greater than equal to 0, y is greater than equal to 0, right? You're in quadrant 1, so your x and y values are positive. If we then get to the inverse function of this, right, y is equal to root x. So many of you will be fine with this, no problem. Notice how x and y have swapped around, but the domain and range is actually essentially the same because we're working in quadrant 1. Okay, so same story here. Here we're just looking at the negative x values. When you get to the inverse, all right, notice how it's not plus or minus, hey? When you've got that restricted domain, and you square root, it's not plus or minus. You need to consider, right, where am I working? Am I working with the positive x values in the positive y-axis or negative x values in the negative y-axis, vice versa? So here we can see that when you had the negative x values, when you switch the inverse, you now are going to have negative y values. Swap x and y around. In the first example, it didn't matter because we were working in quadrant 1. Right now, though, we can see that that definitely has an effect. So here they just showed you swap x and y around. So it's these last two that I really want to discuss. So y is equal to negative x squared. Your y values are negative, but the x values are positive. When you switch to the inverse, all right, you get y is equal to positive root minus x. So here, because there are restrictions on the domain and range, it doesn't matter that you've got that negative under the square root sign. So we're saying don't worry about it. It's fine. You are correct. It's a handy tip to write down the domain and range of your original function to help you determine the domain and range of your inverses. So, you know, like if I put this stuff down and maybe you can't remember like which arm is going to be where, like how do I know that the inverse of this is drawn like that? Putting down the domain and range of the original function makes your life easy, because now when you've got the original and you swap x and y around, so now you know, okay, so I want negative x values, but positive y values. So then you'll know that that's the little portion of the arm that you're going to draw. And the same down here. If your y values are negative and your x values are negative, switch x and y around, we're obviously going to be in the same quadrant. So that's the same as the first one where we're working in quadrant 1. The domain and range is actually the same for the function and the inverse. All right, so don't worry about these negative under the square root signs. And remember that if you do have restrictions, if you do chop off a part of the parabola or a part of the original function, remember that when you square root, it can't be plus or minus, right? You need to see, am I working with the positive or the negative part of the original function? And lastly, we're just going to touch on the exponential and logarithmic graphs just to, make sure that we've consolidated everything in this section. And these graphs are actually pretty cool and pretty easy to draw. So if I just draw y is equal to 2x, right, we know that it's not going to have an x-intercept since the asymptote, right, the value of q is 0. So the line y equals 0, the x-axis is its asymptote. It will have a y-intercept of 1, so that would be your graph y is equal to 2 to the x. If we just talk about the reflection of this graph, so let's do some reflections. If I were to reflect this graph over the y-axis, so when you reflect over the y-axis, what happens is you multiply x by a negative. We could rewrite this as y is equal to 2 to the negative x, or y is equal to a half x, right? It's going to be 2 to the negative 1x, which we then write as 1 over 2 to the power of x. So this is a decreasing exponential graph. Our first green graph was the increasing exponential function. This y is equal to a half x is the decreasing exponential function and looks like this. So it's also going to have a y-intercept of 1, and the asymptote is also the x-axis or the line, y is equal to 0. So this is the exponential graph, y is equal to a half x. Okay, so they like to test this quite a bit. Like here's the original exponential graph. What is the reflection over x-axis? What is its reflection over the y-axis? Now, what is its reflection over the line? Y is equal to x. Remember that this coordinate over here is 0, 1. So when we reflect over the line, y is equal to x, remember what happens is x and y switches. So if we start with the first green graph, so I'm going to do its inverse in blue. So we're going to do the inverse of this one first. So if we switch x and y around, x is equal to 2 to the y, so therefore y is equal to log 2x. If the y-intercept was 1 for the exponential graph, the x-intercept will be 1 for the log graph. And this is what your graph will look like. All right, so you'll notice here that this was an increasing exponential graph, right? Do you notice that its inverse is also an increasing function? So that's important because let's compare it now to when I look at the decreasing exponential graph. So let's just quickly label this. This is y is equal to log 2x. So the decreasing exponential function, now we need to draw the log graph for that function. So we'll do that in red over here. So we have y is equal to, we need to switch x and y around, hey? So it's going to be x is equal to a half to the power of y. So therefore, y will be equal to log a half x. Some people write this as negative log 2x. By the way, they're both saying the same thing. And when I draw this graph, so like I said, the increasing exponential function had an increasing log graph. So the decreasing exponential function will have a decreasing log graph. So it will look something like this. Right? Also passing through 1 as its x-intercept. Okay, so yeah, this is all drawn just by hand. So I've tried to make it accurate. It's, yeah, looking pretty good. But yeah, that just wraps up your exponential and log graphs. Remember, writing down the domain and range for the functions are also so important because it helps you then when you have to work out the domain and range for your inverse. So for example, these first two graphs that we drew here, right? The domain for these would be, okay, x can be any value. There's nothing which restricts your exponential graphs left to right, hey? There's no asymptotes left to right, but we do know that the range is affected by the asymptote. So the range is y is greater than the line, y is equal to 0. Y is greater than 0. If you now compare that to the domain and range for these chaps, right, for your inverse functions, just switch x and y around. So now there's nothing that restricts your red and blue graph up and down, right? So their range is y is an element of real numbers. Switch x and y around. Its domain, so from the y-axis, the line x equals 0 has become the log function's asymptote. So its domain will be x is greater than 0, right? Or if you weren't looking at the graph, just swap x and y around. Okay, so that would be the domain and range for those functions. All right, grade 12s, well done. This has been, it's been a lot of fun. Just recapping all of this with you. The stuff that we work through is really basic. Obviously, our working through past paper questions and exam style questions is what's really important, which we'll be covering soon. And yes, thank you so much for tuning in and listening, and I hope you enjoyed the lesson.